Today we're going to talk about the force of gravity, and to start our discussion, I'd like you to first draw the free body diagram for, I don't know, let's just pick a falling ball. So I'm going to go ahead and, as usual, this is the object that's falling, a little dot representing the center of mass. And if the ball is falling, first we have to discuss some non-contact forces. What is in contact with the object? Well, first of all, there's nothing in contact with the object except for air. We're going to ignore air resistance. But there's still a non-contact force due to the force of gravity, which we know is going down because it's always going down. So I would go ahead and draw a force of gravity like that using lowercase g, always lowercase, to indicate the force of gravity. And then if I use my normal problem-solving technique, my next thing that I would do is I would write my F total equals mass times acceleration. And then I would look at my free body diagram, because that's what I drew in order to figure out the total force, and I would see that the only force acting on the object is the force of gravity, and that has to equal mass times the acceleration. But I already know the acceleration of this object since it's falling. We talked about in the last unit. The acceleration of that object is 9.8 meters per second squared, otherwise known as g, which is the acceleration due to gravity. So I see this really, really important equation, which we're going to see and use a lot, that Fg is equal to mg. And I can use this all the time. And this is a very common equation that we're going to use. People tend to forget it, but what it says is that the force of gravity, wrong thing to draw there, so I'll just do a little undo. What it says is that the force of gravity is equal to the mass of an object times the acceleration due to gravity. This is also known as weight. So the force of gravity is equal to the weight of an object. But our weight, the weight of anything that we calculate, is not going to be measured in pounds. Weight is going to be measured in newtons, just like all of our other forces. That's a really key concept to remember. The other thing we want to remember is that the force of gravity is not the same as mass. So Fg does not equal m, because we know Fg is equal to m times g. So for instance, if we have an object with a mass of, let's just pick 80 kilograms, we could find the force of gravity on that mass, because we would just take 80 kilograms times 9.8 meters per second squared, and we would get 784 newtons. Now, another thing that we want to remember is that mass stays constant regardless of where we are in the universe. But the force of gravity will change depending upon our location. So I'm just going to put this, I'm running out of room, so I'm going to put this up here. So mass is constant of an object throughout the universe, because mass is the matter that makes you up. So if you go to space, you don't change mass. You don't lose any mass, right? You're not losing an arm. You're not leaving behind a leg. You're taking all the matter that makes you up with you. So your mass doesn't change as you go throughout the universe. However, the force of gravity does change. So weight does change, because that's going to depend upon g. And g is different on different planets and in different locations. So we're going to have to keep that in mind as we do these problems as well. So let's go ahead and let's take a look at a sample problem that might involve weight. So we have a 12 kilogram box being pushed with a force of 40 newtons to the right on a rough surface. So we're going to assume 5 newtons of friction, but we're going to assume that there's no air drag. So in any of our example problems that we're doing right now, we're going to assume no air drag. So the first thing we're asked to do is list all the forces acting on the box. The easy one is the force of gravity. It's always acting 100% of the time, unless we are so far away from Earth that it can't. We know that there's going to be a normal force because the table is, or the rough surface is pushing up on the object. We know there's going to be a force of friction. So I'll just put that FF. And then I also know there's this applied force applied. So those are the 4 forces that are acting on the box. The next box, we're going to be asked to draw a free body diagram, so I'm going to go ahead and draw the dot. I know the force of gravity is acting down, and I know the normal force is acting up. And I draw those the same size because I know the object isn't jumping up and down off the surface. So the forces in the vertical direction must balance each other out so that there's no acceleration in the vertical direction. In the horizontal direction, however, I know I have this applied force, and I can just put F applied is equal to 40 newtons. And then in the opposite direction, because I know friction acts in the opposite direction of sliding, I know that the force of friction is equal to 5 newtons. So there's my free body diagram. In the last box, box C, they ask, what is the acceleration of the box? So I drew my free body diagram, so my next step is always to write F total is equal to mass times acceleration. The whole reason I drew the free body diagram is to figure out what should I plug in for that F total. I know the normal force and the gravity force are going to balance each other, so I don't have to worry about them. So it's just the other two forces. So the total force, I just add up all the forces, so I have 40 newtons. And I'm not going to add that 5 newtons because I know it's acting in the opposite direction to the applied, so I'm going to subtract that. 40 newtons minus 5 newtons is equal to the mass of the object, which I know is 10 kilograms, times the acceleration, which is what I'm trying to solve for. So 35 newtons is equal to 12 kilograms times acceleration. I can divide both sides by 12 kilograms, and I should come up with the acceleration being 2.92 meters per second squared. I know it's to the right because I know the larger force is acting to the right. Now this next part of the problem is kind of interesting. It asks, if the pusher wants the box to accelerate at 4.3 meters per second instead, what force would the pusher need to apply in the box? So the free body diagram doesn't really change, it's just that I don't know the force applied. So I'm going to go ahead and still write my F total is equal to mass times acceleration. Since I don't know my applied force now, I'm going to go ahead and write F applied minus that 5 newtons has to equal the mass, which hasn't changed, times the acceleration, which I now know, and I want to be 4.3 meters per second squared. So my applied force is 5 newtons plus whatever 12 times 4.3 is, 51.6 newtons. So I get 56.6 newtons for that applied force. Now we finally get to the new part of this problem, which is when we're asking about the force of gravity. People forget our equation, but I have to remember that the force of gravity is always equal to the mass times g. I know my mass is 12 kilograms times g, which is always 9.8 meters per second squared, as long as we're on Earth and pretty close to the surface. And when I do that math, I do indeed get 117.6 newtons. Now we said earlier when we drew our free body diagram that the normal force is equal to the force of gravity, so this I don't even need to do any calculation. I can just write down that the normal force is equal to 117.6 newtons. And that's how I'm going to use that equation for the force of gravity. I also want to be careful. Force of gravity is not the same as the acceleration due to gravity, so I'll never use the term gravity. I will either say force of gravity or acceleration due to gravity. I won't just say gravity. I think you should adopt that habit as well. That's it for today. Have a good day.